where it began. I can't begin to know it, but then I know it's going strong. Hands, touching hands, reaching out, touching me, touching you. Sweet Caroline,
bum, bum, bum.
good times never seem so good. I'd been inclined
Bum, bum, bum.
to believe there never would, but now I...
Go, Daddy!
Alright everybody, welcome to this week's edition of Video Notes for AP Chemistry. That's right folks, this is going to be for AP Chem. And we're starting a new unit here, you guys. It's actually about something called thermodynamics. But we're going to start off with some basics about heat and chemical reactions. Now to start out with, I'm going to assume some things, because you guys are smart people who have taken a lot of science classes. So I'm going to assume that you know this. You know the difference between endothermic reactions and exothermic reactions. Remember, the endothermic would be reactions that feel cold. Okay, exothermic would feel hot. Okay, exo means they release heat. Endo means they take it in, right? Now, so I'm assuming that you know what kinetic energy means, right? Kinetic energy is the energy of movement. And that you can tell the difference between potential and kinetic energy, right? Kinetic energy is movement, potential is stored. Alright, so let's talk about this, okay? Heat versus temperature. So heat is a form of energy, right? And we measure that in joules. This is what we measure energy in. And oftentimes you will see this too. You will see it measured actually in kilojoules, because joules are quite small, okay? Temperature, on the other hand, is a measure of the average kinetic energy of particles in a system, right? For this, we're going to use the Kelvin scale. Remember, kelvins are degrees Celsius plus 273 gives us kelvins, right? Now, here's the cool thing about the Kelvin scale and why we do it. By the way, got a little typo here. Sorry about that. When the temperature doubles, the energy doubles. So it's proportional here, right? When our temperature doubles, we get twice the amount of kinetic energy happening in the particles in the substance. So something to be aware of as we start talking about this is something called the Boltzmann distribution, okay, and how that relates to temperature. So here's the deal. We've got this fancy-dancy graph over here, right? And basically what it shows is this, right? It shows the actual temperature, and then the bell curve there, right? I guess you'd call that sort of a parabola, right? It's upside down. Shows the distribution of the average kinetic energies of the particles in the substance. Okay, so basically what this leads us to is this: as temperature goes up, we get a greater variety of kinetic energy, right? So we have lower temps, we have a lower variety, right? When we have higher temps, we have a greater distribution of kinetic energies. However, when all this is said and done, right, average kinetic energy increases with temperature. All right. Now this is something you need to be aware of as we're going through this unit. We have two things involved. We have the system, that is the actual chemical reaction that's taking place. Okay, so for example, if we are just doing this simple reaction of hydrogen gas plus oxygen gas, giving us water. Let me balance that out real quick. Okay. That is our system right there, the gases and the water vapor that is produced. Then we have the surroundings. Okay, the surroundings is everything outside of that chemical reaction. In other words, the entire universe. Okay, so the system and the surroundings. The system is very specific. The surroundings is everything else. Okay, so we need to talk about energy transfer. In this case, we can talk about heat. Okay? Because heat is energy that can move, right? So here we have two systems, okay? And if you notice, they're in thermal contact, right? So that means that energy can move both this way and that way through the central barrier there that has the two systems in contact. So what's going to happen, right? So here's the initial, the before, right? Energy will transfer from this. Energy will transfer from high temperature to low temperature until equilibrium. And apologize for my writing. That's equilibrium right there, you guys. Okay, till equilibrium is reached. So here you can see this, right? Eventually we reach a place where the temperatures of both systems are the same. Now what's happening is this, right? Because we have energy being transferred here and we have a higher temperature at 450 kelvins, energy moves from this system here over to this system here, right? What type of energy is transferred? This is heat, right? Or we could also say this, it's also kinetic energy, right? Okay, because what's going to happen is the kinetic energy on this side will go down, and the kinetic energy on this side will go up. All right, now here's one of the real fundamental ideas in science. It's conservation of energy, right? So we know this, right? You can't create or destroy energy. However, we can transform it into different forms. Okay? That's kind of important. So that means this, when we have a system, right? Energy changes anytime one of three things happens, right? One is this, when we have a chemical reaction. When we have a chemical reaction, something's going to happen to the energy in that system. It's either going to go up or down. When the phase change happens, right? Melting, boiling, freezing. We could also put in here evaporating or condensing. Okay, both of those things will change the energy because that is a phase change, isn't it? You also have this, right? A change in temperature. Obviously, that is going to change the energy of the system. So the big deal is this, right? Because the energy of a system changes anytime we have any of these things happen, right? That means the energy has to be transferred into or out of the system. So the question is this, right? What forms does it take when it goes in or out, and where is it going, right? How much? Those are the big questions. So we have two ways that we can either bring energy in or get rid of it. One is through work, which we'll talk about in class, and the other is this, right? In the form of energy, specifically, this is in the form of heat energy. Okay, so heat can move in and out of the system, or the system can do work, or have work done on it. We will address both of those issues when I see it in class. Well, I hope you guys have a good day. Thanks for tuning in, and we'll see you first period. Bye-bye.